Hello, everybody. How are we doing? Afternoon of day 3 of the conference. Energy levels are at an all-time high, I hope. In all seriousness, though, it's been a really, really great couple days. Lots of really engaging presentations, and we're really excited about our manufacturing industry breakout today. Excited to be welcoming one of our most strategic customers to the stage to talk about their journey. My name is Alex Amato. I lead customer services at C3 AI. Been with the company since 2015. It's been quite a journey. Right around the time I joined was actually when we began working in the manufacturing space. Really expanded our area of focus from the energy and utility world, where we were exclusively focused for our first 4 years or so across industries, and manufacturing was a natural next step for us. And so really, a majority of our application innovation has all been very relevant and specifically focused on manufacturing for many years now. We, in the manufacturing space, have a portfolio of applications that have specific domain models and capabilities designed to help manufacturing companies, like those represented in the room here, to scale to meet the needs of manufacturing specific problems across the value chain. And we work with many customers around the world, some of those here really across different product areas, industries, and these over time have further allowed our product to accelerate innovation and improve to allow for industry-specific capabilities that can be genericized and modularized in ways that allow all of you here in the room and all of our customers around the world in the manufacturing space to, again, meet very industry-specific needs with these applications. I'm excited today to welcome Sergio Barrios, Vice President of Data Science and AI from Pantaleon, to the stage to talk about their journey with C3 AI in the area of production optimization. Sergio.
Thank you. Thank you so much, Alex, for the introduction. I'm Sergio Barrios. I worked in the sugar industry for about 21 years now. Most of my experience has been in the electronics department, meaning control systems in the factories, in the plant floor. So most of my time I spent, capturing and analyzing data. And we began this journey about 4 years ago with our digital transformation project. And of course, you want your investments to have an ROI, right? At the end of the day, when you have all this technology and all this data available, you want to make good use of your data and get value from that. So we went into a partnership and this project with C3 with the hope of having leverage on that data and get value from that. So I'm going through one of the pilots that we did, which is the PRO pilot. It's a process optimization. We've been doing other pilots with scheduling and also with Gen AI. But today I want to present to you the results that we had during this journey. And most of all, that you understand the changes in paradigms that we had due to these applications. Most of the guys here today are from the sugar industry, I can see. So I will stay humble and say that we're still learning. We do not have all the answers yet, but that's precisely the purpose of this. We're still learning and trying to improve our systems, right? So I'm going to begin with a brief introduction of Pantaleon. We are a sugar mill. We are a group. We have presence in 4 different countries: Guatemala, Nicaragua, Mexico, United States, you name it. We produce sugarcane from sugarcane. One of the main objectives of this pilot was to minimize the losses or maximize the yield of the sugar from the sugarcane that is available for the factories. And we started this pilot in one of the sugar mills, the largest one, which is located in Guatemala. I would say this right away. We started with a very ambitious project, which is tackling the largest factory in the group and trying to get the maximum value of that. Later on, we've learned some lessons that I will share with you. But of course, one of the aspects that you need to take into account is how much are you getting, how much value you're getting from your projects. But there are other stuff that you need to take into account, like, is it feasible to do that? Do you have the data? Is it a tractable problem? Do you have the expert knowledge you need, not only from the business side, but also from the technological side? And this is why we see C3 as a very strategic partner for helping us reach to that goal. So I will try to explain you the scope of the problem. This is a very simplified schema of a factory. Very, very simplified. I'm sorry for you guys that are experts on this. But as you see, it's a process, it's a serial process that begins when the sugarcane enters the first mill and ends with crystallized sugar. And this is the way we operate. We have a serial process, and there's a team of people that is in charge of every process. This is a traditional way of looking at it. If you see here, we have a global KPI, the most important KPI, that summarizes all the activity in the factory, which is the global recovery. And it's basically how much sugar are you able to recover from the sugar available in the sugarcane. And this is the scope. We said, well, we want an AI app that could help us minimize the losses. I mean, there's a finite amount of sugar that is available at the start of the process, and we want to minimize the losses during the industrial process, the manufacturing process of the sugar. And if you see here, this is the business perspective. You have three phases there: the extraction part, the juice treatment part, and finally, the sugar recovery, where the sugar sort of burns. So we said, and this is the business approach, let's optimize each phase, right? And this is the way it's done in reality. You have a head of the extraction department, you have a head of the juice treatment department, and you have a head of the sugar recovery process. So let's optimize that, and let's build an objective function, let's say, something that measures what we want to improve, and let's optimize for that. And this is the traditional approach, right? So when we started to define the scope of the problem, we came up with different hypotheses. One of them was, well, there are thousands of different configurations that a process can have. Which one is good? Which one is the best one that you can have at a certain specific time? And most of the time, you will rely on operator experience, on expert knowledge. Even in science, you have equations that describe your process, and you can have those as a guide. But the problem is really more complicated than that, meaning that in a certain period of time, you have to control for your constraints. And the constraint definition is not something that is so obvious. You might know what they are, but to measure them, to know what they are specifically in a period of time is very hard. And I will give you an example. We have equations that describe the juice extraction from the mills or the juice treatment clarification. But what happens if, for example, in the last 2 days, there was a very serious storm, and this storm just flooded all the fields, and this led us to have problems with dirt and mud in the process. Your equations might still apply, but the conditions change a lot in the process. Dosage of chemicals should increase for you to maintain the quality, but how much? And this is something that is not very obvious to do. You have to somehow take into account the knowledge of very experienced operators, the knowledge of the managers, and take a decision on what to do. And this is a very dynamic process. So by the time you take the decision, maybe the conditions already changed. So this is the challenge that we faced. How to react fast, and not only react, predict what's going to happen, and with the given conditions, what's the best decision that you can take. And that's the whole problem of optimization to now. So this is what we wanted. We wanted to have a common foundation for the data, laboratory data, lab data, which tests the quality of the sugar, the sugar cane, of course. We want information about the process. How do you connect the PLCs? How do you connect the computers that are registering in real time what's happening in your process? How do you connect the production databases? When you have the finished product, you have testing about the quality of the sugar. How much sugar are you producing? So that's a very ambitious goal, having an end-to-end application to optimize the whole factory. So this is what we learned with C3. Of course, you want to tackle this one step at a time. You cannot, of course, you will want to have everything at the same time, but somehow you need to have a starting point. And what we did is we took the phase optimizer approach. And what this means is that we started from the beginning of the process, trying to optimize that, and then grow that optimization application by updating constraints and variables over what we did in the previous phase. So as you see here, and the difference is that phase 2 contains phase 1. It's not separate. You don't optimize by segments. You do it based on what you did previously. So here's a simplified schema of that, where there are a phase inside another phase. And when you end at the last phase, you achieve your goal. You optimize every step of the process, and you updated the constraints. And why this is important is because in a certain period of time, your decisions in one process might affect the performance of the next process. And you guys might know this, but when you're trying to analyze or do predictive models, these processes are very, very tricky to tackle, and it's because there's a principle that does not hold here, and is the independence of variables. What you do in one process affects significantly the next process. So you might think of it as confounding variables when you're trying to analyze these kind of problems, but also lets you connect those. So it's a problem from the predictive side, trying to find independent variables to predict the outcome of a process. But it's also helpful because it helps you define what the new constraints will be when you optimize the next process. So this is what we did in the phase optimizer approach. And then we get into the real world. And this is where it gets fun, right? When you're trying to get a model to operate in the real world, you see that not everything is ideal. And what I mean by that is that you have sensors in the plant. You have, in the factory, you might have thousands of sensors. Those sensors are prone to failure. They might have uncertainty. Or even there are other kinds of equipment that are installed that will lead you to think that certain constraints do not hold. And in the case of a continuous process, some of these constraints are related to physical constraints, which are the mass balance equations, right? This we know that holds. And somehow the data will not always reflect that because the sensor will have uncertainty, will have error, will sometimes cut off. It just fails. So for the optimizer to work, you need to make sure that the readings you're getting are, first of all, possible or feasible. And second of all, have a chance to follow the constraints. So this is what we have here. We have a two-stage optimization approach. The first one, let's say, calculates an equivalent of the variables that will follow the mass balance equations. And let's say you have a sensor that has 2 or 3% error, meaning that sometimes it's 2% above the real value, or sometimes it's 2% below that. You don't know. There's an uncertainty in that. So in that specific time, you don't know what the exact value was, but we can try to minimize that error because we know that the mass balance equations must hold, so we optimize for that first. Meaning that if you have a sensor, and it's very important, that sensor for the predictive model, for the optimizer, we calculate an error, which is, in this case, a squared error, based on the deviation from the mass balance equations. So this is what connects us with reality. What your real sensor is saying might not be the exact value that goes into the optimizer, but we know that over time, that sensor should reflect reality, which is the mass balance equation. So the first step is to start from a feasible point. In the feasible region of the optimizer, we start from a feasible point that is dictated from these mass balance equations. When we minimize that error, then we take those inputs into the next phase, which is the objective function. I'm not showing here the whole objective function. Just know that it's composed of optimizing the yield at each process by minimizing the losses. And the losses are measured by, first of all, the sugar content of the byproducts. Those who are familiar with sugar production know that there are byproducts that are being produced by each process. And we want to minimize the sugar content in those byproducts because that's the way the sugar reaches the end of the process. But there's another variable that is not very obvious or easy to control, and it's the amount of byproduct. And the combination of both of this, the amount of byproduct and the sugar content in that byproduct, determines how much are you going to lose in the process. And the optimizer is capable of seeing both. We have nearly 50 predictive models, 15 different machine learning models that take care of the sugar content in the byproducts, that will take care of quality measurements. Of course, you might minimize the amount of byproducts you're producing at the expense of the quality, and you don't want that also. So there are predictive models for the quality also. We have quality measurements like transmittance or turbidity or color that are embedded in the machine learning models and lead you to define constraints. So you don't reduce the amount of byproducts at the expense of the quality. But also, and this is a big important finding that we did, is that people tend to operate in the safer side. Of course, if you don't have all the inputs you need to operate at the optimum, you tend to operate on the safer side. What this means is that, for example, an operator which has a goal of achieving certain quality of the sugar will tend to adjust the dosage of a chemical on the safe side, meaning that I will apply a little bit more just to make sure that my quality is okay, it's on the right side. But this decision of the operator of increasing the dosage also leads to more byproduct, and therefore more losses. So this is where it gets tricky. Until what point? How much can I reduce my chemical dosage? How much can I reduce the water in a system? It's very hard if you don't have all the information. Even if you do, there are too much variables to analyze. So this is what the optimizer does. This application has nearly 800 variables. And can you imagine monitoring 800 variables and taking a decision every 2 hours, analyzing the last 2 hours, and taking a decision on how to do the next step? It's almost an impossible task. And added to that, how do you maintain the vision, the global vision of the process? How do you decide to sacrifice one part of the process in order to get to a global maximum, a global yield? It's very hard. And this is the change of paradigm that I was talking about. I will get into that in a few minutes. So we did a very hard job, I would say. We managed to come up with, right now, this is a work in progress, of course, but we have 7 different set points across all of the factory. And this is the thing. You need to follow all of them at the same time. You cannot say, I will follow just the first one, the first 2, and then the other one I will not follow, and so on and so forth, because the optimization is carried on end to end. So you need to follow all of them at the same time. Otherwise, you might end up in a suboptimal position, and you won't want that. So right now we have 7 set points. We are working on expanding that. But below these 7 set points are 700 variables. And among those, there are 70 that are crucial. And what I mean by crucial is that we need to make sure that they are high quality, they are coming at the right rate, and let's say there is someone responsible for that information. And that's very important because you're using here data to take decisions in almost real time. It's not something that you want to look at the next day in a report or a dashboard. This is something that is very, very fast. The cycle is very, very quick. So how does this work? Right? Because this changes the way we usually do things in the plant floor. We need a new workflow for that. And that workflow might conflict from what you do right now, meaning that some of the orders, so to speak, or the recommendations come top down. The manager or the head of the process just sees data, usually from the last hour or the last day, and gives a recommendation to the operators, and the operation see if they are feasible, and they follow that. And they operate that for, I don't know, a shift, 8 hours or whatever. Here, there is an optimizer that is working, recording the data, updating the models, the predictive models, and the optimizer is being run by every 2 hours. So every 2 hours, a new recommendation is generated. So how do you make sure that the operators are following that? So you need a workflow. You have a shift process that is on the plant floor that sees the recommendation. And now, if you see here, we're keeping a human in the loop in the first stages, of course, to see if that recommendation is feasible or not. Meaning, is it possible to add that amount of water? Does that chemical dosage make sense for the quality of sugar that we're doing right now? Or the water that we're adding to the centrifuge is safe for the centrifuge to operate? Will that generate a lot of molasses? So this is where we try to involve all of the levels of the factory into the decision. We try to explain what the optimization works, what information is taking into account, trying to explain to them why it is important for their feedback on that, because this system is continuously learning. So what happens is that an engineer is helping us going into that and through those set points. They say, I will accept them and will send that to the operators. So the operators who they have a better view of the plant floor would say, okay, this is the recommendation. It is possible because I have the conditions of the factory, all my equipments are online, so I will just go ahead and implement those in the control system or directly in the process. And that's why we keep that human in the loop right now, because the optimizer, there are certain variables that are not visible to the optimizer yet, related to reliability of the equipment, and so on and so forth. But once they are accepted, the system records that the operator accepted the recommendation. So this serves two purposes. The first one is we calculate an adoption rate. And this is very useful when you do change management. You want to make sure that the operators are following the recommendations. Otherwise, you cannot assess the performance of the optimizer. And the other purpose is we need to know when the optimization didn't fail, when we get it right, okay? So there's a reference there, sort of like a picture of the conditions under which the optimization got it right. And this allows the data scientists, the application developers, and of course, when we want to improve the process, to know when things went well, where were the conditions. Or if they were wrong, why they were wrong. So we have a certain field there where we can write some feedback. Like, for example, we couldn't add this amount of water because, I don't know, it's dangerous for the mill, or it will have dissolved the sugar crystals. Any kind of information is very helpful. So next time, we might find a new constraint that we didn't think about and implement that right back into the optimizer. And next time, it will not make that mistake. Okay? So what about the results? As I said, this is still on process, but this is a very good way of assessing the success of these applications. Is how do you measure how much are you getting, how much value you're getting from the application? If in the future you're operating with the app, maybe you don't have a baseline to measure, to compare with, right? Because you're already operating with the app. So what we did here is somehow back test what would have happened if the application had worked in, for example, the last 6 months or the last season. And why are we able to do that? Is because we have the predictive models that have very low error. So if we input all the variables into the predictive models, we know what would have happened if we have followed the optimizer recommendations. So we run the optimizer with historical data. And the optimizer said, well, instead of doing that, I would have done this other thing. We'll have these other set points. And based on these other set points, run through that same predictive models, what would have been the yield, right? So it's just back testing and getting into the loop the optimizer. How well will the optimizer will have done if it will have been operating in the last year? And this is what we get. Somehow a 2% increase yield that will happen in the last harvest. And you see here that it follows somehow the natural curve or trend of the process, which has its ups and downs. Is this accurate? Well, we should see that in the next harvest. But this is just one perspective of the process. What I mean by that is that we're feeding the predictive models and the optimizer with process variables, flows, temperature, pH, levels. But there are other things that are not taken into account. The equipment availability. When you do plain shutdowns for maintenance, and all that other stuff that will be taken care of with the reliability pilot. But this is just an idea of how to measure the yield. Finally, I will just share with you some takeaways of our journey, some learnings that we had. These are not technical, so don't expect something technical. If you need technical details, I'll be glad to provide that to you. But these are more on the paradigms that we have. All right, this you might have heard for other projects. Just begin with the end in mind. Have a clear objective of what you want to get from the application. Like I said, in the beginning, we began with a very ambitious mind. Then we get more realistic goals as we progress in the development of the pilot. But beginning with the end in mind will help you understand where you are right now, in the technology aspect, in your people competences, and what you want to achieve. And this will help you have better and realistic plans. The other takeaway is that you might get a little bit frustrated at the beginning, and this is very common because most of the factories are not used to operate this way. So it's a learning. It's a learning journey. So to keep the teams motivated, you need to celebrate the progress. If you do small wins, you should celebrate the small wins. Of course, we want the big wins. This is what we all want. But big wins are, built over progress. So every time you're making progress, just make sure that your teams are motivated and let them know they're doing the right thing. This is something that we need to accept. Sometimes you're going to fail, right? And this is something that we've learned, sometimes the hard way. But failure is not that bad if you learn from what you did wrong. So there are many lessons that are to be learned when you're trying to implement this. And most of them have to do with management systems that you might already have in place, how much the operators are following recommendations, why they are not following that. As long as you learn from what you're doing wrong, you can improve that. So don't get frustrated. You'll get there. Sometimes you need to be patient and persistent. And if you want to do an app, just think about you're building something that improves over time. You are learning, your operators are learning to use the new tool, and this new tool will gain knowledge from feedback that you're providing to it. So it will get better and better over time. So don't be frustrated at first. This will get better as the system and the people together improve the process. And the last one is be open to change. As I said, at first you evaluate or you assess your projects based on the economical value you're getting or you want to get. But there are other considerations, technical considerations, if you have the data to do that, and so on and so forth. Sometimes the idea you had at the beginning changes a lot during the journey. And that is not bad. It's just you getting more knowledge on what you're capable of doing. One might say, tackling the whole factory as a first attempt, it's a lot. It's very ambitious. And you're right. We might have been doing well with fewer variables, with a smaller objective. But at the end of the day, if you optimize one segment of the factory, you're not getting really the global optimum on everything. And this is why it is important to have, at least at the first attempt, know the scope of what you're doing. And this is why we decided to do it end-to-end. Because otherwise, it will be harder to incorporate other processes later on the journey. And this means that you might encounter that the way you were doing it was not right. And it's not bad. It's just you're learning, and you might want to try new things, different things. I already explained to you the workflows. We expect these workflows to be improved over time, but this also implies a change in paradigms, in control paradigms. The way you're measuring your operators. You cannot measure your operators by the single KPI they were measured before. Because the optimizer is looking at everything. So you should think about it. It's not the same KPIs you're going to measure the operator performance, right? And finally, if you need to let go of something that you know is wrong, let it go. It will just cost you more at the end. And it's better to say, well, that wasn't the route I should have taken. Let's change that. And don't be afraid to do that. It will save you some time and money at the end. Well, thank you very much. I appreciate your time.